Hey everyone, and welcome to this Forge College Explainer. I am absolutely thrilled to have you here today. So if you've been following along with our EVM to SVM transition track, you know we've been working steadily towards our capstone project. In the last module, benchmarking and data collection, we spent, a ton of time running controlled scenarios, capturing telemetry, and honestly gathering some really beautiful raw CSV files full of transaction samples. Well, today is the day we actually put those CSVs to work. We're going to build a scenario-ready cost model, one that puts our gas-based and compute unit-based measurements onto a perfectly even playing field. But right out of the gate, we've got to acknowledge the absolute absurdity of the core problem here. Okay, on the EVM side, we measure everything in gas. On the SVM side, we use compute units. Trying to compare these two raw outputs directly, it's literally like trying to compare gallons of gasoline to watts of electricity to figure out who owes who for lunch. You just can't do it. They represent completely different resource accounting paradigms. And that, my friends, is exactly why we need to build a universal cost translator today. So here's our agenda, the master blueprint for the mechanical spreadsheet, or Python script if that's more your jam, that we're assembling today. 1. The Universal Translator Challenge. 2. Calibrating the baseline assumptions. 3. Building your cost calculator. 4. Sweeping for sensitivity. 5. Finding the break-even point. And 6. Validating your machine. Let's get to it. Section 1. The Universal Translator Challenge. Our mission here is to transform these raw alien metrics, our gallons and watts, into a single language that we can actually use. To do this, we rely on a very specific definition, the normalization factor. Think of this as the magic gear in our translation machine. It's a multiplier constant used to map raw protocol-specific measurements into a common unified cost unit. This is the whole shebang that makes our apples to oranges comparison mathematically possible, bridging the gap between raw blockchain mechanics and actual economic modeling. Moving right along to Section 2, calibrating the baseline assumptions. Before we even think about turning our calculator on, we need to calibrate the dials. We do this by creating a dedicated assumption sheet. Check out these constants. For EVM gas, we might set a normalization factor of 0.001 cost units per gas. For SVM compute units, maybe it's 0.0008, and we can't forget transaction size, an I/O surcharge of, say, 0.00002 per byte. Now listen, what's crucial here is that you never want to hard-code external price feeds directly into your formulas. No way. These numeric entries are derived directly from your benchmark data and your agreed-upon protocol pricing surrogates. They absolutely must remain as named inputs so we can easily tweak them later. Okay, Section 3, building your cost calculator. So we are finally ready to assemble the actual math engine. Here is the sequential blueprint. First, we import those cleaned CSV files from our previous benchmarking module, specifically txsamples.csv and run telemetry.csv. Second, we add that assumptions sheet we just talked about, making sure our named variables are locked in. Third, we normalize every single transaction row using our constants. And fourth, we aggregate the data per operation. We do this by grouping the feature tags we instrumented earlier, which gives us the mean, median, and 90th percentile costs. And this right here is the core mathematical equation that powers the whole translation process. Normalized cost equals your raw gas times the norm_gas constant, plus your compute units times norm_cu, plus your transaction bytes times IO_byte. You really want to treat these cell references like the vital thermodynamic connections of an engine. Oh, and a quick tip. If a benchmark row is missing a column because it was protocol specific, like say an EVM row having 0 compute units, just treat that missing column as a 0. Keep the formula uniform across the board. Now we've got to scale this thing up. Knowing a per transaction cost is great, but what we really want is the monthly cost per user. To get this, we multiply our newly aggregated per operation costs by the expected transaction volume for a user in a given month. Then we look at the one-time costs, stuff like state rent, storage initialization, or account creation. We take those one-time costs, divide them by our assumed amortization window, meaning how many months we want to spread that initial cost across, and sum it all together. Boom! Just like that, you have a highly accurate, scenario-driven per-user cost estimate. All right, Section 4, sweeping for sensitivity. This is the fun part, where we get to stress test our newly built machine by just forcefully turning those calibration dials. The technical term is sensitivity analysis, which, yeah, sounds incredibly intimidating. But let's de-jargon this. It really just means systematically varying your assumptions, wiggling those normalization factors up and down to see what breaks or what drastically spikes your total costs. Like, if you increase the cost of EVM gas by 20%, does your total per user cost skyrocket? Does your wallet catch fire? Sweeping helps us pinpoint exactly which features and usage patterns are our primary cost drivers. Which brings us to Section 5, finding the break-even point. Let's figure out how to find the exact spot where our EVM and SVM scales perfectly balance out. For a given transaction mix, we want to solve for the exact normalization ratio that makes the average per transaction cost identical on both chains. The algebra here is pretty straightforward. The break-even norm Gauss factor simply equals the SVM norm underscore Q factor multiplied by the total underscore Q, all divided by the total underscore gas. Honestly, if you're in a spreadsheet, you can literally just use the goal seek feature to find this without even breaking a sweat. 0.00092. In our specific benchmark example, this is the exact magic decimal that perfectly levels the playing field. To put that into perspective, if the actual cost surrogate for gas drops below this number, the EVM framework becomes cheaper for our specific transaction mix. If it goes above it, the SVM framework is cheaper. It's a beautifully precise target to have. And finally, Section 6, validating your machine. Our machine is built, the dials are calibrated, but before we ship this operational annex for our capstone project, we absolutely must ensure it actually works. So I want to pose a provocative question to you. Does your newly built machine accurately reproduce the raw benchmark data? Because listen, if you can't trace your modeled estimates all the way back to the raw CSVs, your model's flying blind. We need rigorous testing. Let's run through our baseline validation checklist. Number 1, check your data ingestion. Ensure your schema and column names match exactly. Number 2, the normalization sanity check. Literally pick 3 random rows and do the math by hand to ensure the calculator isn't dropping parentheses somewhere. Number 3, aggregate reproduction. The scenario averages in your model must match a raw SQL query of your CSV. Number 4, monotonic behavior. Basically, if you increase the price of gas, the total cost shouldn't magically go down. And number 5, substitute your break-even number back into the model and make sure the totals equal out perfectly. You can only save your file as baseline validated once all 5 of these pass. Before we wrap up, I want to leave you with the absolute golden rule of cost modeling. Separate measurement from valuation. Your measurements, those raw benchmark CSVs, are immutable historical facts. Never edit them. The valuation, your normalization factors and amortization windows, belongs completely isolated in an assumptions configuration sheet. Keeping this structure ensures your scenarios remain endlessly auditable. So what does this all mean? The crucial takeaway is that you now have a working model that translates alien metrics into real impact. Your next step is to export that scenario summary and prep for actual optimization testing. But I'll leave you with this. If your new cost model proves that migrating to an SVM framework makes your protocol 100 times cheaper, are you bold enough to actually rewrite your entire dApp tomorrow? Really think about that. This has been a Forge College Explainer, and I hope it helped illuminate the mechanics of cost modeling. To master more Web3 engineering topics and see this curriculum in its full context, definitely head over to forge.college. Keep experimenting, keep testing your assumptions, and I'll catch you in the next one.